and welcome. Thanks for joining an excellent safety webinar. Today we will tackle one of the most frequently asked questions about safety switches and interlock doors. What performance level, or PL, do I need? I could simply answer, PLD will do. While that is true in many applications, there's much more to the performance level than just the safety switch alone. Therefore, let's pick up the story from its beginning and clear the riddles about door safety switches and the performance level.
This webinar will answer 3 questions. What is the PL or performance level? Which factors influence the PL? And how do I determine which PL is needed for my door solution? Let's answer these questions one by one. Consider a simple machinery system as an example. To prevent people from entering a hazard zone, you will often install guards. But for maintenance and troubleshooting, you need doors, lids, or flaps to enter. The machine behind the guard should not run when the doors are open. The door is fitted with a safety switch, which interlocks it with the machine function. When someone opens the door, the machine will stop immediately. And while the door is open, the machine cannot start. The safety switch could also have a guard locking mechanism. Guard locking prevents opening of the door while the machine is running. To enter, the operator must first press a button to tell the machine to stop and then unlock the door. Both interlocking and guard locking are safety functions. As long as these functions work properly, operators are safe. Therefore, safety functions must be reliable. But not every safety function needs the same level of reliability.
That's a bit strange, isn't it? Shouldn't safety equipment always be reliable? Yes, it must. But it's also quite clear that the higher the reliability will be, the bigger the price tag. So should the designer simply go for the cheapest, or should he always select the most reliable solution possible? What could be a reasonable basis for making that decision?
To answer that question, consider an important safety system of 3 different types of vehicles. The brakes. A bicycle has 2 mechanical brakes which are not monitored, but it's unlikely that both brakes will fail at the same time. A car has 4 brakes in 2 separate brake circuits that are both monitored by the car's control system. If one circuit fails, the car will tell you, and modern cars will not start if a brake failure is detected. A large passenger airplane has 4 or more brakes with multiple brake discs. Each is monitored by several independent safety controllers for wear, temperature, blocking, and many other factors. No way could an airplane start unless all brake systems function properly. Why these differences? The difference simply is in the risk potential. Only one person rides a bicycle, and in an accident, likely no more than 2 people will be injured. A car may carry up to 5 passengers, but in an accident many more people may be injured or even killed. Car accidents can also cause considerable property damage. The largest passenger airplane, the Airbus A380, may carry up to 853 passengers. The brakes work only on the ground, but if they don't, hundreds of people may be injured or killed, and dramatic damage will occur. What has this got to do with the PL? The PL, or performance level, is a measure for the reliability of safety functions, and it depends on the level of risk. To the bicycle brakes, we might assign a low PLB or medium PLC. For the car braking system, PLD would be reasonable because it always includes monitoring. And to the airplane, a minimum of PLE should be assigned. In the aerospace industry, however, engineers use SIL to describe the reliability of safety functions. SIL, SIL, stands for Safety Integrity Level. SIL is also used for machinery, but more commonly in process technology, cars, and airplanes. Both PL and SIL define the reliability by setting limits for the likeliness or probability of a failure of the safety function. The higher the risk, the lower the probability of failure of the safety function must be. PL has a range of A to E and SIL of 1 to 4. For machinery, only SIL 1 to 3 are used, however. The reliability of a safety function is expressed as the probability of a dangerous failure per hour, PFHD, where D stands for dangerous. As you can see in this table, the higher the risk, the higher the PL or SIL must be. The last column gives the probability of failure allowed. The figures are quite low. The higher value on the PLD line would mean only one failure is allowed in 1 million hours of operation. That is one failure in 114 years.
From the example of the different vehicle braking systems, we have learned that the reliability of a safety function depends on two important things. Number one, the reliability or quality of the safety components, and number two, the monitoring of their function. That also means that a safety function can never depend on a single component like a safety switch alone. The safety switch must switch off something to make a dangerous function stop. And for monitoring, you would also need at least one additional component. What else is involved?
This simplified illustration shows a common safety function occurring in machinery. The operation of a motor is controlled by a movable cover. The safety function involves three components. 1. The position of a movable cover that prevents access to a hazard zone is detected by a door safety switch. 2. The on-off signal of the door safety switch is connected to a safety relay, which switches number 3, a contactor that controls whether an electric motor runs or not. The three components have different functions. They serve as sensor, logical controller, and actor. These three elements occur in most safety circuits. When I add an emergency stop button, a second safety function results. What type of component is the emergency stop button? Sensor, logic, or actor? You're right, it is a sensor, because it senses somebody in panic hitting the button. The safety function uses the same logic and actor components. Still, it is a second safety function because it is triggered by an event that is different from the first. Finally, I need to add a reset button to reset the stop of the motor. It is not a safety component, however, because safety will not be lost if it fails. So far, the safety function involves only electromechanical and electronic components. But there could also be pneumatic and hydraulic components. I could replace the contactor with a hydraulic valve and the electric motor with a hydraulic motor. Would you say this setup is safe? Absolutely. When the cover is opened, the motor will stop. When somebody hits the emergency stop, The motor will even stop if the cover is closed. But is this safety function very reliable? Well, this setup uses reliable safety-related components. The door switch, for instance, is strongly built and will survive frequent opening and closing. It is not like a micro switch on the lid of a laptop computer. A typical door switch is good for about 6 million cycles. The switch on the laptop will likely last for no more than 5,000 cycles. But there is no monitoring of the components. If the door safety switch is defective, always saying that the door is closed, then the motor will keep running when the cover is opened. Or if the contactor sticks and cannot drop off, the motor will keep running, even if the door safety switch is working properly. One fault in one component can lead to loss of safety. That's not very reliable. We call this a Category 1 safety function. It has reliable components, but its fault tolerance is 0.
We have now learned something very important. The performance level of a safety function does not depend on one component only. If you were to buy a safety switch that can reach performance level D or even performance level E, that does not mean automatically that the entire safety function will reach that same level. The performance level depends on all of the components used in the safety function and the way they interact. Sounds a bit complex? Let me make our safety function a little more reliable. That will help understand.
I will add a second door safety switch or a dual channel safety switch. In the safety relay, I will use 2 separate inputs for the signals of the safety switch. Is this safer than before? Many feel tempted to say yes, but it is not safer, only a little more reliable. How so? The safety relay can now detect a failure of the door safety switches by comparing what they say. They should both simultaneously say that the cover is open. If they say different things, the safety relay will cause a stop of the motor and not switch it on again until the fault is resolved. However, this is only slightly more reliable than before. Why? A failure in one part, here the contactor, could still cause loss of safety. If it sticks, the motor cannot be switched off, no matter how many door safety switches the circuit has. Therefore, this safety function still meets no more than PLC or SIL 1. To increase the reliability substantially, the redundancy needs to extend through the entire safety circuit. To achieve that, I will add a second contactor and an auxiliary contact on each contactor. The auxiliary contacts are connected to the safety relay, so it can read the switching status of each contactor. If one fails to switch off when the cover is opened, the other still works, so the motor will stop. However, the auxiliary contact of the failing contactor will report the fault to the safety relay. The safety relay in turn will prevent the machine from switching on again until the fault is resolved. Is this safer than before? Again, the answer is no. It is not safer, but it is a lot more reliable. The safety relay can now detect the failure of the door safety switches and the contactors. In case of fault, it will not allow restart of the motor until the fault is resolved. An accumulation of faults and loss of safety are prevented. This is a Category 3 or 4 safety function. It reaches PLD or E, corresponding to SIL 2 or 3. The degree of fault detection determines whether it is PLD or E. We call that the diagnostic coverage, the contribution of the self-diagnosis of the system to the overall reliability.
but it is safe to forget that term for the time being. From here, the details of the topic are for control system engineers only. If you need to know more, Accident can arrange for an online seminar on control system safety and reliability in both English and German. Let me summarize for the time being what we have learned about performance level or PL.
Performance level PL and safety integrity level SIL define the reliability of a safety function, the safety-related reliability, in terms of the admissible number of failures per hour, and they are determined by all components in the safety circuit: sensor, logic, and actor, and their interactions. Single-channel safety functions can reach no more than PLC or SIL1. To reach PLD or E, SIL2 or 3, one needs dual-channel safety, redundancy, and diagnosis. Of course, the change from single-channel to dual-channel safety with diagnosis comes with a price tag. The more reliable setup will cost twice the amount you would spend for the single-channel safety circuit. Therefore, you should learn to know why and when you need dual-channel redundant safety that reaches PLD or E. Let's now find out how you can determine the PL or SIL you need. The required performance level is determined during risk assessment. We call that the PLR, where R means required. From a recent webinar, you may remember this risk assessment chart. For a given work situation, it finds the hazards and then determines the safeguards to install. Note that the safeguard in the second line involves the control system. It specifies a safety function, monitoring of a door safety switch causing stop of hazardous movements. For this safety function, we need to determine the PL or SIL required. This is done by risk estimation. The method most commonly used by machinery manufacturers is shown here. It is from EN ISO 13849, Part 1, and uses 3 risk elements: the severity of injury, the frequency of the task or operation, and the possibility to avoid or limit the harm. When all 3 have been estimated, the required PL, the PLR, results. EN IEC 62061 presents a second, less well-known method of determining the PLR. It also allows to find the required SIL CL, where CL stands for claim limit. This method uses 4 risk elements and more criteria for each of these. You see them here. The PL is found by first estimating the severity of injury, SE. In this case, 4. The estimations for the frequency, FR, probability of occurrence, PR, and the possibility to avoid, AV, are added to form a class value, in this case 9. The class value is then used to read the result from the left side of the table. In this case, it is SIL2 corresponding to PLD. Estimations with this method are a little more complex, but also more precise. At Accident, we favor this method over EN ISO 13849, Part 1. Now we only still need to enter the result of our risk estimation on the risk assessment report. I will add a column on the right to do that. The risk estimation column now lists the estimations of the 4 risk elements and the result, the required PLR or SIL CL. Following these procedures, you can determine the performance level required for your door safety switch. But bear in mind that in one machine, the level of risk can be different in the individual hazard zones. Therefore, you need to estimate the risk for each hazard zone in your machinery. This is important even if you plan to install the same type of safety switch at all the doors, because the risk determines the required performance level, and the required PL determines not only what type of switch you need, but how to design the safety circuits with single channel or dual channel safety, with or without diagnosis functions.
Thank you for having joined this accident safety webinar. If you need to learn more about risk assessment, go to our website and download our risk assessment guide, which is available in 5 languages. You may also ask for an online safety webinar on the topic. Stay safe with accident.